好的，感谢月游。Hello，大家好，欢迎来到原力区的直播间，我是本次活动的主持人武荣，欢迎大家继续跟随我们探索 Web 3.0、Web 3先行者的系列活动，主要是面向不同的公链，邀约行业资深大咖进行分享和交流。在我们之前的活动中呢，不仅有知名公链，还有依托于不同链的明星生态项目，希望我们可以共同携手，一起共建共享 Web 3生态繁荣。Hello everyone, I'm Dolores. This is our fourth open day of FaaS Web3 community. We are a non-profit community, and now we are having a series of Web3 projects featured on our community. There are not only public chains project here, but also ecological developers and builders rely on different chains. So we welcome everyone to speak out through our platform and promote the development of Web3 together. Thank you for joining us at the fourth open day where we're going to talk about everything Web3 and the future of the internet. We're also a best place to launch or discover the brand new products you have never discovered before. So in the 243rd event of the fourth open day, Alex, a Fluence Lab engineer, is invited as a guest speakers here to share the topic about influence Web3 with Fluence. So 对于Web 3来说呢，最重要的基础就是去部署去中心化的网络。那依靠 Web 3协议和其他的协议来进行一个连接，或者实现一些相互的操作性。那本期的原力开放日呢，将带领大家了解 Fluence 网络。Fluence 就是这样一个点对点的应用程序的平台，然后提供了点对点的开发堆栈，然后可以对 P2P 的这样的应用程序组合和 API，然后直接进行编程，然后也不需要依靠其他的一些中介性的服务。Fluence 的堆栈100%的是开源的，由开发人员社区维护和管理，并且可以提供协议、基础设施和工具来支持网络上面的这些应用程序和后端去进行中心化的计算。So Fluence provides the protocol, infrastructure, and tools to enable this decentralized computer for applications and backend peer-to-peer networks. And Fluence purpose is to build distributed system programming language allows developers to program, distribute networks, and compose a host service into decentralized applications. So as a result, the Fluence protocol and the solutions stack allows you to quickly and effectively create and implement Web3 protocol. So, hey, Alex, it's our pleasure to have you with us today. We love to hear your briefly introduction and say hello to our Chinese audience online.
Hello, thank you for having me. My name is Alex. I'm working at Fluence Labs, doing networking stuff and distributed algorithms and a lot of different things. And today I'm gonna show you how to write some basic Aqua to orchestrate protocols and orchestrate distributed peers.
Okay, awesome. So let's move on the sharing from the Alex. Okay, Alex, please do your presentation.
Yeah, sure.
Okay, we can see. Please get started.
Yeah. So I'm not gonna have any like slides or anything since it's a hackathon. I'm gonna be focused on the code, and I will just show you how to write basic Aqua. We'll start from the very simple things like request response stuff. Well, what is Aqua? Aqua is a language that allows you to describe distributed algorithms on a very high level, right? So it means that you can like imagine that this is the whole peer-to-peer network that we have, and I have my laptop and I want to do something with the network. For example, I want to say, hey, this peer, go to other peers and please tell them to like execute some function. Like goes and tell executed. And this peer says, okay, executes the function and then sends data here. And so far and so forth, we can this way step by step describe different distributed algorithms. For example, some replication, data replication, load balancing, even consensus we can implement like that. But doing this manually in like a language of your choice, Python, Go, Rust, whatever you like, it usually takes a while. Like you have a lot of details, you have asynchronicity, thread pools, resource management, sockets going up and down, and all these complexities that are inherent in usual day-to-day programming languages because they're pretty low level. And in Aqua, we have a syntax and the thinking mindset that allows us all to talk about distributed systems and in code like they're first-class citizens. You just say, hey, go to this peer, this is relay, execute this function, and get me some information back, and just print it on the screen or do something with it. So this is the very, very basic function that goes to some peer in the cloud somewhere in the peer-to-peer network and says, execute this function. And whatever it returns, give it back to me, to my laptop. So this is a very basic request response thing that you could have with some HTTP or whatever. So it's very basic thing, but let's try to actually run it and see if it works. Hopefully it will. So let me show what I'm doing here. I have actually this explained here. So this is an invocation of command line utility that's called Aqua. Aqua is both compiler and a runtime for the Aqua language. You can install it from npm. I hope you already did if you were working on Fluence. If not, I will show how to do that a little bit later. But yeah, that's the main entry point to Fluence right now, to Aqua. So if you want to run some function, you should use Aquarun. Aquarun allows us to say, hey, take this source code, run this function, use this relay for that. And if you want to specify, you can specify a private key here. It's not necessary, but sometimes when it comes to resource control and like deploying services and like managing them, you need a secret key. So I included here just to make it clear that every time you do Aquarun, it actually creates a local peer, connects to peer-to-peer network, and sends the script there in the network. So since it creates a local peer like that, right, it ought to have public key for encryption, for routing. It has to have public and private key, and that's exactly it. So let's run this command and see if it works. Yeah, it works, and what it returns to us, it returns two things actually, as we asked it. I asked it to return info structure that describes the peer, like it says, hey, I have this version of the Aqua language. I have thus external addresses that you can use to connect to me, and this is the version of the Rust peer, also called Node, that I'm hosting. And this is the peer ID of the relay node. So that's exactly what I asked to return, info and host peer ID. We can take a look at the info structure definition here in the built-in Aqua. Built-in Aqua is kind of standard library for Aqua language. So we can see that data structure info contains three fields: external addresses, node version, and error version, and that's exactly what we got here. So we successfully connected to peer-to-peer networks and a very simple script there. It executed somewhere in the network and returned results to us back. That's not very interesting though. Let's do something more interesting. For example, if we want to start describing distributed algorithms, we might want to work on a list of nodes, on a list of peers, right? So let's do exactly that. And instead of a single info, I will now return an array, a list of infos. So I will go to every peer here and ask it to return me information about itself. So we have iteration like that in Aqua for name of the variable, arrow, and the name of the collection. Then we have to say on P. What it means? It means that whatever I write here will be executed on the peer or on the peer P, right? So we have a list of peers. For example, if we take a look here at the network, it could be like that peer, that peer, that peer, and that peer. We will go to each of them and ask for info. So basically what will happen is we'll say send script to relay, and relay on its own will send request here, then it will send request here, then it will send a request like here and here, for example, and they will all return information back. So that's what we're gonna implement. Let's do that. So on peer P, we want to gather info. Let's do it the same way as before, but we will see that it won't work because I promised to return an array of infos, and now I'm collecting just a single piece for every peer. I need some way to accumulate the data and return it. We have streams for that. Streams have this syntax. It's a star asterisk before the type. And what they allow you to do is to exactly gather information from several peers and return it somewhere or do something or iterate over it. So we will write, so we go through all peers in this array. On each peer, we say, hey, give me your identification information. And once you've done it, please put it to the stream that's called infos. And at the end of the function, we will just return the infos stream. Let's try to do that. But there's one thing, like, for example, this function get info, it didn't take any arguments, but this one, it does. So we need to pass them. When we do Aqua run, we need to pass some peer IDs. Where do we get them? Luckily, we have default peers command in Aqua CLI tool that it basically knows a few sets of bootstrap peers that you can use to connect to the peer-to-peer network. It's like in every peer-to-peer network, in Ethereum, in BitTorrent, or whatever, you always need to know bootstrap nodes in order to like connect to the network somehow. So let's take those. We won't need all this information. We don't need, for example, like this is the networking information, like DNS name, port, and stuff. What we need for our case is only peer IDs, because inside Aqua, everything is routed through peer IDs. Nodes, peers themselves, they participate in a discovery protocol that's called Kademlia, and they know how to discover each other just by peer IDs. So let's do a little bit of formatting for that. Yeah, okay. And I will just, and what I'm doing here is just copy pasting the JSON list, because when I use Aqua run, I specify that I want to use basic Aqua file because it's basic Aqua here, right? So, and I want to call function get infos, and I want to pass arguments here, and I want to pass a list. Since it's a JSON list, I will use square brackets and we'll put several peer IDs in there. Also, as I said before, I need to specify a relay to use. For our relays, there is a like shorthand, like stage 02 that tells where to connect. It's just for convenience. Actually, it's a whole multi-address. Okay, so we got a list of responses back, right? It was pretty fast, but as I drew on a diagram, it was still sequential, right? But we got what we wanted. We got the information about every node. And we, for example, here we see that all nodes, they have the same versions because it's like the same set of nodes. And more to that, they are hosted on the same host, because what I'm using here is our staging environment. That's like a test environment for demonstrations and for just testing bleeding edge stuff that we develop and break often. If I would use some other environment, all IP addresses will be different because they are hosted on different computers. Okay, so great, but you can see that the ports are different. Yeah, so that's actually different peers. Okay, great. So we did gather information from several peers and returned it back to my laptop. That's actually kind of a distributed algorithm already on its own. You could, for example, almost use the same approach and like do some weighted average, not obviously on identification data, but imagine that instead of peer identify, you would have like some token price returned, right? You would be able to average those numbers, and this way you will get a very, very basic kind of consensus where you don't trust a lot to each of the peer, but collectively you accumulate, and like the trust accumulates as well. So you can receive information from several sources and average it, and you will have like information that you believe more than in any single peer. So that's already a distributed algorithm, but it's kind of, you know, it's sequential in the sense that every peer executes this sequentially, like first goes the first peer, second goes the second, and Aqua allows us to parallelize this stuff very easily. Let's do that. So it will be almost the same function, still return a list. We will still need to gather the information in a stream, and we will still need to go through all the peers. But there is a difference. We will put a par here, this par instruction. It tells that all iteration should happen at the same time. Like in this case, it's a sequential execution, so every next iteration starts to happening only when the previous one finished successfully. But with par, they will all start at the same time. So let's do that. It's actually a very interesting thing, because could you guess what will happen here? Let's try to run it. We'll just need to like rename this function with all the same arguments. So it's now get infos par. Let's run it. And we receive empty array. Why is that? Because this thing, it started all iterations at the same time. So they executed immediately, and we never got result back. So we basically just done this. In order for this thing to work, we need to wait until all or some of the peers here return information to us. For example, we can do it like this. We have an instruction called join that allows us to wait until there is enough elements in a stream. So for example, we want to wait for 2 elements, right? We would do this. This waits for 2 elements because it's zero-based. Like indexes, it's basically an index. It says, hey, join, like wait until there is an first element in the infos stream, like the element with index 1, and that's like 2 elements, 0 and 1, 2 elements. Okay, let's see where it gets us, how it works. Okay, great. So we asked to wait for 2 elements, but actually got 3. Why is that? Because this thing, it all runs in parallel. It runs concurrently. So we actually, if we rerun it, we might have a different number of results, more, for example. Yeah, we got more, you see? And that's because there is a race here, a very natural one, and I would say intended race. Like I intentionally said, okay, you run all those instructions concurrently, and I only care that you wait for at least 2 elements. If it could happen that while you're waiting for 2 elements, actually more elements get to you, more responses get to you back. That's totally possible. But for example, if we put a very, very big number here, what will happen? Nothing will happen. It will time out. Why is that? Because there would be never this much number of elements in this stream, right? It's going to be always at most the same number of elements as was in peers, and in peers there was like 6 elements or something like that. So how do we modify this code so we don't need to hard code numbers? Luckily, we have here in built-in Aqua, we have service called op. And what it provides different functions. We right now care about this one, about array length. We want to have length of the peers array, and based on that, we want to wait for some number of elements. So let's try to do that. Yeah, and we will pass peers here, and we will subtract 1 from here because it's zero-based. Okay, let's try to run it. Yeah, and it waited for all of the nodes of all of the peers here to respond to us with infos. And that's basically how you can use Aqua to write distributed algorithms. Of course, this is a very simple example, but still it works. And you have all the instruments to make it more and more and more complex. We, for example, have implemented price gating from Ethereum, replication and indexer over IP FaaS. And we have just a multitude of examples. I hope you know about them already. If not, they're in the repository Fluence Labs /examples. There's a lot of examples, so we try to keep them all working, and we sure succeed at that. So if you ever feel a need to see how some rather complex things are already implemented in Aqua and Fluence, you should check out the examples. They're great. And I guess my timings come to end near now, right? So I guess I will stop. But if I have five or more minutes, I could talk more. So let me know. Do I?
Wow, thanks, Alex. Yeah, thanks, Alex, for the amazing presentation. And we really learn a lot from this. And as Alex mentioned, and as we know, modern cloud computing platform provide many useful service and tools that help build applications. However, relying on cloud-specific tools and processes traps customers in closed ecosystem, resulting costly and risky. As many companies have realized, switching application to another cloud provider or their own infrastructure took a lot of time and resources. So the Fluence stack frees developers from tools by replacing tool sets with open source alternative and turn cloud platform into hardware delivered component that can be changed at will. So, and protecting information from tampering with blockchain technology is used for some digital value use cases such as cryptocurrencies and decentralized finance, NFT, or DOS. So additionally, Fluence complements the blockchain platform with off-chain capabilities, and it brings the next generation of internet computing, which is permissionless, scalable, and composable. So what's more, Fluence is useful for all types of applications currently living in the cloud, such as the web applications, distribute backends, and communication software, and LOT. So we're really looking forward to say Fluence will have more development in creator economy. So before we move on, I'd like to briefly explain for our audience. So就像刚才 Alex 给我们展示的那样，就是展示了一些技术的东西啊。但是我们就是在我们自己对之前的一些 Fluence 的以 Fluence 对战的了解呢，就是 Fluence 它的就是通过开源的替代品去替换专有的工具集，并且将云平台变成可以随意更改的这种硬件。什么？Wait me a second. 感谢我们的后台小姐姐处理了一些问题。那就是 Fluence 它可以将开发人员从专有的工具中解放出来，并且通过区块链技术保护信息不被篡改，并且用于一些数字有价值的用例，比如说加密货币或者去中心化金融以及 NFT 和 Dapps 这些非常有用。那此外呢 ，Fluence 也是通过链下的一些功能去补充了区块链平台，可以支持数据预言机，然后将区块链节点之间更好的连接，并且带来不需要许可，然后可扩产和可组合的下一代互联网计算。最重要的是 Fluence 适用于目前生活在云中的所有类型的应用程序，例如 Web 的应用程序以及分布式后端，还有通信软件以及物联网啊。那 Fluence 也是有助于构建任何优先考虑用户数据隐私和可组合性以及就是可扩展性的去中心化应用程序，所以我们非常期待 Fluence 在创作者经济上面会有更多的发展。So I'm going to move on to our panel and move more about our Fluence. So Alex, we do have some questions for you today. Welcome to join us for the Q&A. The first question is, why did you choose P2P as the underlying architecture, and how do you understand the P2P computing layer aided by Fluence? Alex, could you please answer this for us?
Yeah, sure. Thanks for a great question. Well, peer-to-peer is a most general network architecture, so any other architecture could be built on top of peer-to-peer, so that makes it a pretty natural choice. Also, it allows you to interact directly with hosters, with those providing services, with developers, and everyone, users, developers, hosters, deployers, everyone can communicate directly without any one in the middle. So that's two main reasons. Yeah, and peer-to-peer computations, they change the way that we do computations in the sense that there are no intermediaries, and you can just like take a function and execute it somewhere on the network. And if it doesn't work, you can always choose another peer, and you can write distributed algorithm that goes through several peers and choose the one that works well for you and executes computation on all of them if you want. So yeah, it's a very flexible, very general architecture that enables you to avoid intermediaries if you don't want, or have them if you desire so. Hope that answers the question.
Great, that's really awesome. So compared to Web2 toys, Fluence provides much more flexible with regard to application design, high security, and the greater scale. So P2P architecture allows appliances to connect users directly to each other and keep sensitive data under use control. And so I think Alex gave us a great answer. And before we move on, let me explain to our Chinese audience. 就是 Alex 刚才也有提到，与 Web2 的工具相比 ，Fluence 在应用程序设计和更高的安全性以及更大的规模方面提供了非常大的灵活性和改进。那 P2P 架构也是允许应用程序直接将用户彼此连接，然后将敏感的数据保持在用户的控制之下，然后它可以容忍网络停机的这种时间，然后也更加容易开发管理和让用户社区不是那种就不会依靠于集中性的开发公司这样子。那数据停留在它就是所有者手中基本上也消除了一些故障或者是依赖其他的一些风险。所以 Web3 的这个世界也是致力于去中心化身份存储和域名和加密货币等等的一些项目的呈现。So let's move on to the next question. Compare with other program development platform, what are the unique advantage of Fluence? Alex, could you please answer us?
Yeah, sure. Well, so what we do at Fluence is you could call it a distributed virtual machine. So it's a notion of being able to scatter different computations across a peer-to-peer network and have and orchestrate them in a permissionless and open way. So while you, on the one hand, you can develop useful applications and backends for them, you have an open network on the other hand. So anyone can join and anyone can build their own protocols, and you can like integrate different protocols between each other and like authorize, okay, people who use these are also able to use this technology at the same time. And you can share different resources and documents between people. And that's pretty unique thing. There are no decentralized and permissionless workflow languages, and Aqua gives you exactly that. So, for example, for researchers on distributed algorithms, it's now possible to just take the existing infrastructure and think only about the algorithms instead of going through months and months of infrastructure struggles. You can just write complex algorithms right away as you write a scientific paper. Or if you're app developer, you can take different existing components, stick them like building blocks together, write a replication or load balancing or backupping on top of them, or use existing one, and you will have a distributed application with distributed backend and with decentralized one if you want, so others can join your protocol. And you wouldn't depend on any cloud, and you can use commodity hardware, which is cheap, or you can use high-end hardware, which is fast, whatever you decide. So yeah, that's like pretty unique position of both being open to any kind of computing, being cloud agnostic, and providing open and permissionless tool for managing security of your backends. And on top of all that, using this as primitives, you can write distributed algorithms. Yeah. That works really well for example, off-chain computations. If you have some on-chain part, but you want to do something off-chain, you can just do that with Fluence. Hope that answers the question.
Yeah, great. That's really perfect. So thanks, Alex. And let's move on the next question. The third question is for Dapps in Web3, which type of application direction are you most optimistic about?
Yeah, that's a good question too. So there are several kinds of most popular Web3 applications right now. First of them is DAO. And for DAO, Fluence can provide a way for DAO to pay and manage the infrastructure, pay for and manage infrastructure. For example, imagine that you can say, okay, I want my own version of YouTube, and I want to pay for it for not with my like credit card by a single human who, if disappears, the whole YouTube thing stops working. I want to like have a community around me that pays for that together and makes decisions together. For example, we can have a DAO that decides, okay, we need to update our software there, and it issues voting on blockchain, and the voting results are streamed to Fluence, and Fluence reacts to them, and Fluence automatically executes Aqua script that updates the software or adds more computing to your YouTube or whatever you want. And so that's an information stream from blockchain to the infrastructure management, and you can even pay to people for like doing supporting maintenance jobs for you. So that's all possible with Fluence. That's about DAOs. Another big like struggle in Web3 is when you have some game or any other like an NFT website or anything else that has a lot of logic on chain, but also has a big off-chain part. It sometimes and usually happens that, okay, we have this game on chain, but big part of it is actually in Amazon or on Google Cloud or somewhere else in some cloud that's paid by a single credit card. And if that disappears, the whole front end or back end, they goes down, and all decentralization kind of becomes impossible because yeah, it works on chain still, but users can't go there. They cannot really reach your contracts because your front end or back end doesn't work because it was centralized. So with Fluence, it's possible to, if you have backends, to deploy them on Fluence and decentralize them, distribute, have a load balancing on top of them, and manage them through DAO even. So you could have several things at once. And that solves the problem of having off-chain backends and front ends for Web3 applications. Yeah. For example, if you take like dynamic NFTs on Fluence, it's possible to build a backend that would react to some off-chain events and re-render your NFT, and it will change every time, I don't know, something happens on GitHub. You do a commit on GitHub, you do a pull request, and your NFT changes, and you can like show it to friends. And all that logic, right now, if you do implement this, it should live in some cloud or on your computer or somewhere, but it got to be, most likely it would be a single place, and that's a single point of failure. That's basically centralization. And on Fluence, you can have such a backend implemented and deployed and scattered across the peer-to-peer network. So that solves a centralization problem for such a backend.
Yeah, thanks, Alex. 刚才 Alex 也有提到，就是他比较看好，比如说像 NFT 啊、DAO 啊之类的。那我们也是期待Fluence 将会在这些方面也是有更多的一些合作和发展。So thanks, Alex, again, and we do hope your projects will have more development and collaborate in the future and in different fields. At the last, let's stay tuned and catch up with the development of Fluence. So thanks, Alex, for today's amazing sharing about what you have done, and take care. See you next time.
Thank you very much.
好的。
Cheers.
拜。好的，就是再次感谢 Alex 今天的到来和精彩分享，让我们期待在2022年 Fluence 在更多的领域有进一步的发展和合作。那非常感谢来到我们原力开放日的嘉宾的这个，大家也可以看到，就是我们持续不断的 Web3 先行者，然后得到了大家很多的支持。那后续呢，也将继续为大家带来有趣的话题和分享，然后和生态资深大咖的一些交流。欢迎关注我们原力区的公众号，加入 Telegram 和 Discord， 在社群内与我们互动交流，精彩活动第一时间知道。谢谢大家，我们下周2再见。Thanks everyone. We do hope you have a great day here with us. So see you next time.